All right, everyone. I'm going to go through the two, I guess I'll call them physics examples for our vectors thing to wrap up 12.2. So, oftentimes we use vectors to represent forces because a force has a magnitude, normally expressed in pounds or newtons, and a direction. You can have multiple forces acting on something, and if you want to calculate a resultant force, all we need to do is a vector sum of these forces. So that's pretty straightforward when you're just asking to find a resultant force. That's what example 7 is going to ask for us to do. Suppose two forces are applied to an eye bracket. The first force has a magnitude of 200 newtons and makes an angle of 30 degrees with the positive x-axis. The second force has a magnitude of 300 newtons and makes an angle of 70 degrees with the positive x-axis. We're going to find the magnitude and the resultant force and angle that it makes with the positive x-axis. So if you don't have a picture, I generally recommend drawing a little sketch here. So let's draw a set of axes, x and y. Say we have a force vector, let's name it F1. We'll call this vector right here F1. It makes an angle of 30 degrees with the x-axis, and we know that the magnitude of F1 is 200. For our second force vector, that makes an angle of 70 degrees with the positive x-axis, and we know that it has a magnitude of 300. So all we need to do to find the resultant force, which it's going to be somewhere between these two vectors, because if they're both pulling kind of up and right, I know that I'm going to have another vector that's kind of pulling up and right. It's going to be probably a little longer because we're going to combine forces. That's pretty strong because they're kind of going similarly in a similar direction. We need to represent F1 and F2 with a vector, and then all we have to do is add them together if we want to find that resulting vector. So I will call the resultant force just F, which we know is going to be the sum of F1 and F2. We're going to use our definition from above to define F1 as 200 times cosine of 30 sine of 30. We can actually simplify that by hand. It's 100 root 3 and 100. F2 is 300 times the vector cosine of 70 sine of 70. That one we can't simplify by hand, so I'll leave it for right now as 300 times cosine of 70, comma 300 times sine of 70. So to get our resultant force, all we gotta do is add those two together, component-wise. So that's 100 root 3 plus 300 cosine of 70 degrees, comma 100 plus 300 sine of 70 degrees. Now, if you'd like to see some decimals with this, which is not a bad thing for any of these real-world applications, if you plug that stuff in your calculator, I get approximately 275.81, comma 381.91 for our resultant force vector. Now, if I want to find the magnitude of that, that's pretty straightforward. The magnitude of F, we're just going to take both of our components, we're going to square them, add them together, and take the square root. If you do that, I'm hoping you also get approximately 471.09 newtons. Now to find the angle, we're going to be using trigonometry as we do for most of these things. You can use any of the trig functions, but I'm going to use cosine. Why am I going to use cosine? Because when you use inverse cosine, that always gives you an angle between 0 and 180. And that's kind of what we want right now. So we know that cosine of theta, if you're thinking about the angle to wherever this new, I keep writing F1, F vector is, if you think about cosine, adjacent, hypotenuse, our adjacent side is how far we go in the x direction. And what's our hypotenuse? That's going to be our magnitude, which is that value that we calculated for our newtons. And if you take the inverse cosine of that thing, that will give us our angle. And assuming I did it right, you can double check me. I'm getting about 54 degrees. Now, for the second question, we have a 100-pound weight hangs from two wires as shown below. We're going to find the tensions, the forces, T1 and T2 in both wires and the magnitudes of their tensions. So the key to this is understanding what that weight is doing. That weight we can think about as a vector and think about where it's pulling. It is pulling directly down. Okay, so we know that T1 and T2 need to counterbalance if it's hanging up there. Counterbalance the weight. I'll call the weight, we're going to use it as a vector, so let's do our vector W. What is our vector W? We're actually going to take this point where the weight is hanging and we're going to treat that like the origin. So this weight is pulling directly down and its weight is 100 pounds. Think about that like its magnitude. So I'm hoping it makes sense to you that we can actually define that weight as 0 in the x component because it's pulling straight down. And because it's pulling down, it's going to be negative. And to make sure the vector is 100 long, it's going to be minus 100. So if T1 and T2 need to counterbalance this, that means when we add those two vectors together, they need to be equal to 0, 100 because that opposite force right here will keep that place where the weight is hanging stagnant. It's going to stay there if the weights counterbalance each other. So let's start building T1 and T2 because that's what the question is asking for. So T1 over here on this side. If you remember some of your geometry facts, alternate interior angles, that angle right there is 50 degrees. But if we're thinking about the angle we make with the positive x-axis, we're going to use our angle of 130 for T1. So we're going to do the magnitude of T1, which we don't know, times our vector cosine of 130, comma sine of 130. Using some, I guess maybe unit circle or even odd function facts or co-function facts, you could also have used an angle. For cosine, you would have had to have done negative cosine of 50. And for sine, because it's in the second quadrant, sine of 50 would give you the same answer. You could use either of those. For our vector for T2, we're going to do the magnitude of T2 times this angle right here to the T2 vector is 32. Alternate interior angles again. So that's going to be cosine 32 comma sine 32. Okay. Let's make our lives a little bit easier. Let's call T1 the magnitude of T1 and T2 the magnitude of T2. Let's define that so we don't have to keep writing that every single time. So what do we know about the resulting vectors T1 and T2? They have to add up to the vector 0, 100. So we're going to use that fact. We know that 0, 100, that vector needs to add up to, this vector is going to be a little long to write, so I apologize. Negative T1 cosine 50 plus T2 cosine 32, comma, T1 sine, sine of 50 plus T2 sine of 32. So what do we get from here? Sometimes this ends up being a system of equations. I guess it is a system of equations, but for us, the easiest one to start with is this first component because it has to equal 0. You can see why I was using that negative cosine of 50 thing. It's going to leave us with no negative signs that we have to deal with here. We know that 0 has to equal negative T1 cosine 50 plus T2 cosine 32. And from that, I think it should be clear to you that we could do some rearranging. I'm going to solve for a T2 here. T2 is going to be equal to T1 cosine 50 over cosine 32. We can now take that value and we're going to substitute it into a second equation we can come up with, which comes from the second component. T1 sine 50 plus T2 sine 32 needs to add up to 100. I'm going to replace T2, so we get T1 sine of 50 plus T1 cosine 50 over cosine 32 times sine of 32 is equal to 100. Please use a calculator. Be careful here. I'm going to factor out T1. I'm going to show you exactly what T1 is equal to. T1 is equal to 100 over sine of 50 plus, I'm going to have a fraction inside of a fraction, which isn't always great math, but if you're just typing this into a calculator, it doesn't quite matter, does it? So it's going to be equal to that guy right there. If you want it to look a little bit nicer, 100 over sine of 50 plus cosine 50 tangent of 32, which is approximately 85.64, and that's going to be pounds for this question. How do we find T2? Well, we have that definition up there ready to go for us. So T2 is going to be approximately, 85.64 times cosine 50 divided by cosine of 32, which I get to be approximately 64.91 pounds. And those are our magnitudes. So we can now finally end this problem by defining our vector T1. You're going to take 85.64. You're going to multiply by that negative cosine 50 and sine of 50. And I think you should get approximately, because I guess this is all approximate, negative 55.05 comma 65.60. That should make sense. This means the vector is going left, and that means it's going up, and our vector T1 is going in that direction, so that's good. T2, we need to take our 64.91, multiply that by cosine 32 and sine 32 in each component to get approximately 55.05, and our y component is 34.40. So there we go. There are your two physics-based questions. I hope they go well. The homework, there are some questions similar. They might extend these ideas a little bit. Do as best as you can with them. Thanks for watching.